Hello students, welcome to the next lecture in the course Statistical Modeling for Business Analytics. Today we are going to start on the topic linear regression with multiple regressors. So far we have looked at linear regression with a single regressor in order to introduce the idea of what regression is or what errors are and the population regression model. But the more common way a regression model is defined is by including several regressors. So this is what is our next topic. So in this lecture, the outline of the lecture will be like this. First, we will talk about omitted variable bias. So when we do not include more than one variable, we may be causing an omitted variable bias in the estimated parameters. So we are going to look at that. Next, we are going to look at the concept of causality within regression, whether we can say that some independent variables. So far we have been looking at the correlation between y and x, but can we actually use and find causality. Then we are going to see multiple regression and OLS. So we are going to try to see how we can estimate the regression coefficients using the ordinary least square methods. Then we are going to look at the measures of fit of the model, which has many regressors in it. And finally, we are going to again look at the sampling distribution of the OLS estimator so that we may be able to test certain hypotheses about the estimated parameters. So first, we are going to introduce the idea of omitted variable bias. As you know, in the model that we have estimated, we defined a regression model where the dependent variable yi is given as a linear function of xi, beta 0 plus beta 1 xi plus ui. So this ui is, since it's a stochastic relationship and not a deterministic relationship, after we actually find a linear combination which is given by beta 0 and beta 1 x1 I, we still have some error that is left over. So yi is equal to, when we estimate the equation from a given sample of data, we may estimate the equation like this. We have the estimated beta 1 hat and beta 0 hat parameters, and we have x1 I plus ui hat. So this ui hat is after you have built a regression model, the errors that are left over are known as ui hat. Now this ui hat may further have two different components. So one component may consist of certain variables that you forgot to include or you did not include in your original model, which you should have included, and then there is the residual error, truly random error, which is given by, we say vi to distinguish from ui, and this vi is actually random, and this is what is left over after you have taken into account the effect of x1, x2 and x3 on y. Okay, so this is what is this kind of a model where you include x1, x2 and x3. This is known as a multiple regression model. Now the question is, why do you want to include other variables? What is the utility of including other variables? So one of the important reasons why you may include other variables. One of the reasons may be that you actually want to understand the variation in y better, and you want to include all the explanatory variables so that you get a very good understanding, or you get a very good description of linear description of y. So when y is given as beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, then when this part of the plus, of course there will be an error left over, this part of the model is actually, you have made it is a linear combination of these three parameters, x1, x2, x3, where the weights or the weights are beta 1, beta 2, beta 3. These are estimated from a given sample. So the error that will be left over when you have taken into account all the explanatory variables, that will be truly random. Now if you do not include these x2 and x3, then the simple regression model that you might get, which is beta 1 x1, this beta 1 may actually be biased. What it means is, it may be larger than, or it may be smaller than the true beta 1, the beta 1 hat that you get, larger than or smaller than the true beta 1. Since you are trying to estimate the true beta 1, having a biased estimate is not good for you, because you are trying to understand the true effect of some explanatory variable on the y-axis. So you want to get such a estimate which is really close to the population estimate. But if you have a bias in the estimate, then obviously you think that x has a higher or a lower effect on y, and that will get you to draw erroneous conclusions from your model, and that may have a large effect on the policy decisions that you take. Okay, so this is why it is important to see that you get an unbiased estimate. So how can you know that if there is an biased estimator? So the bias in the OLS estimator that occurs as a result of an omitted variable, factor or variable, is called the omitted variable bias. So this is the definition of omitted variable bias. The bias occurs in the estimated coefficient beta 1. This is important to remember. The bias is in the estimated coefficient. Okay, you want to get at the true beta 1. Your aim is to arrive at the true beta 1. You are making an estimate, and when you have not included the other variables, you might get a biased estimate of beta 1. So there are two conditions that is necessary for this bias to happen. One is that the variable that you have not included, which we have been talking of as x2 and x3, but in this slide they are talking about it as z. So you had dropped z from the original single variable regression, but in the multivariable regression you added z. If z that you had originally dropped is a determinant of y, that means z has an effect on y, and z is also correlated with x. Okay, so if these two conditions are met, then you may arrive at a biased estimate of beta 1 hat. So both of these conditions are necessary. So you have to remember this, and in the course we will come back to this concept over and over again of the omitted variable bias, and both of these conditions have to be met for the omitted variable, for the estimate to be biased. So let us look at a particular example. We were looking at how student-teacher ratio has an effect on the test score. Okay, so the test score was your dependent variable, was a function of the student-teacher ratio. Now there may be other variables that you have not included other than the student-teacher ratio. Say one of those variables is the English language ability, that is whether the student has English as a second language. So people who speak English at home, for them English will be a first language, but people who come from different kinds of ethnic backgrounds, they may not speak English at home, so for them English will be a second language, and as a result they may not be so proficient in English, and this may actually affect their ability to do well on standardized tests which are obviously in English. So suppose the variable that you have not included is English language ability. Now this does this English as a second language, does it meet both the conditions? That is, English as a second language, does it affect test scores? And second, is it true that the correlation of English as a second language and the student-teacher ratio is not equal to 0? That is, could it be that the English as a second language and student-teacher ratio are somehow correlated? So, as we can see, English language ability affects standardized test scores. Someone who is not very good in English, who have English as a second language, their test scores might be lower. So, the first condition is met. Secondly, it might be that those same communities which have a large concentration of immigrant population, in this particular case they are talking about California, so the particular immigrant population they are talking of may be people who come from Latin America and they speak Spanish at home, so they have to learn English, so they speak Spanish at home. So such immigrant population, they may typically live in districts which are somewhat lower income districts, and they may send their children to schools where the class sizes are somewhat larger, because they cannot afford to send their children to schools to more expensive schools which may have smaller class sizes. So in fact, English schools which have larger number of students which have English as a second language may also have larger student-teacher ratio, and hence the correlation between English as a second language and STR is not equal to 0. So this will probably be some kind of a positive number. So since both of these conditions are met, beta 1 hat may be biased. Okay, so what does your common sense say? That could beta 1 hat be biased? So you can think about that a bit. So what is beta 1 hat? Beta 1 hat is the estimated effect of having small class sizes on the standardized test scores of that school. So let us look at the formula for beta 1 hat. So the formula for beta 1 hat is equal to the true beta 1, the true population beta 1, plus the standard deviation of the error divided by the standard deviation of the independent variable multiplied by the rho xu. Now, where is this formula coming from that that can be derived, and we are not going to look at it. Formula can be derived, okay, but basically what this formula says is that as the correlation between the included x's and the errors, remember that the error has two parts, z and the true random errors. Now if u is correlated with x, maybe this part, the z, that was the variable that was left out, that is correlated with x, and this is not correlated with x. Okay, but even if one part of u is correlated with x, u is correlated with x. As the correlation between x and u increases, that is the included variable and is correlated with the error that is left over, then the correlation, then the bias will be higher. That is, it deviates from the true beta 1 population by a larger amount. So this is the bias, and the bias is higher when the correlation is higher. So for example, districts with fewer ESL students do better on standardized tests and also have smaller classes. So ignoring the effect of having many ESL students factor would result in overstating the class size effect. You may actually be thinking that it is because people are attending higher larger classes, that's why they are doing poorly on the standardized test, but it may not have anything to do with the larger class sizes per se, but it may have to do with the fact that they are also also having to learn English as a second language. And since both of these coexist in the same schools, you may be attributing the lower test scores to one variable when it should really be attributed to the other variable. So if we sort of discretize, or if we look at our original data of student teacher ratio, if we do not take the continuous variable but we put it into categories. So what are the categories? In the columns we are putting, these are small class sizes. So this column talks about small class sizes, and this column talks about, this is the large class sizes. Okay, this column is the large class size. Meanwhile, on your rows we have the first row talks about all districts, but below that the school districts have been categorized in terms of the number of English learners that are there in that particular school district. So this is the first category, which has very low percentage of English learners. Okay, so when it has very low English learners, that means people in these school districts actually are better at English. And then you have slightly increasing English capability, and finally a slightly decreasing English capability, and this particular category of schools has very large number of English learners. So over here this is high English as a second language kind of schools. Now let us look at what is going on in the test scores. First, you will notice that within small class sizes and within large class sizes, if you look across the English learner groups, there is actually quite a variation in the test scores. Okay, so for within that group of small class sizes, if you look at schools which have both small class sizes as well as low English learners, they are doing quite well on the test scores compared to the mean of that group. And here also in this particular category, again in the large class sizes also, they are doing quite well compared to the mean of the entire large class section. So in both of these cases, when English learners is small, they are doing better than the mean. And in fact, what we see that in this particular category, if you look at the difference in test scores between small and large, so you are trying to see how much effect large class sizes have, we in fact see that the large class sizes are doing slightly better. So the difference is negative over here. So here you cannot really attribute any changes in test scores to the size of the class. Rather, it is completely attributed to the fact that they are better at English. Now if you look at, as you go further and further into categories that have higher numbers of English as small second language, you find that the differences increase over here between small and large class sizes, till it peaks over here. So it is 5.2 over here, and then it again dips to 1.9. What does this mean? That in groups where people are already struggling with English as a second language, over there in fact, if you have smaller class sizes, over there for those particular groups, smaller class sizes make sense, and rather than having larger class sizes. So these are students that are already struggling with English. In those particular cases, the smaller class sizes means that the teachers can give further personalized attention to the students and probably help them achieve greater success in the standardized test scores. So you can see that actually there is an interaction effect that is going on between the size of the class and whether whether the students in that particular school are having difficulty with English or not. So are we actually attributing, when we do not take the English as second language variable into account, and we say that the difference between small and large class sizes is equal to 7.4, are we actually attributing greater weightage to smaller class sizes than we should? As we can see, in each of these cases the difference is less than 7.4. So are we making a mistake when we say that in fact reducing the class sizes has a large effect on the standardized scores? So this is what we are saying. When it is larger than average, that is what we are saying is a omitted variable bias. Now we come to the interesting idea of causality and regression analysis. So in econometrics, many times what we are really interested in is the causal relationship between two variables y and x, or how much of, if there is 1 unit change in x, how much of a unit change or how much of a change is there in y. This is because x's are often policy variables that the economists can control, and they are really trying to help. So for instance, if you are trying to reduce inflation, then you may try to increase the interest rate. Okay, so interest rate is a policy variable, and what you really want to have an effect on is the inflation. You can't directly control inflation, but you could try to use monetary policies. So this learner's example shows that if an omitted variable satisfies the two conditions for omitted variable bias, then the OLS estimator in the regression omitting that variable is biased and inconsistent. So this is important to remember, that the smaller regression, where you have not considered the z variable, the estimates of beta hat that you have got from that smaller regression may not be accurate estimates. So how do we define this beta 1? How do we define this estimated beta 1 hat that we are trying to estimate? So this is what we are going to look at, several different interpretations of beta 1 hat. So what are we really trying to estimate? One is the very simplistic mechanistic idea that we want to, suppose we have a cloud of points, we may very mechanistically we might say that we want to find that line which passes through the middle of this cloud of points, and we are really interested in looking at the slope of this line, okay, and the beta 1 hat and the intercept of this line, that is beta 0 hat. This is a very mechanistically way of looking at the regression results, okay. But sometimes we are not really looking at it just as a slope, especially when you have 2 or more variables, then it is not easy to visualize the beta 1 hat as slopes of a plane, or a slope of a line, or slope of a plane, or something like that, when you have many variables. So what is beta 1 hat then is what we are trying to look at. So sometimes we want to make forecasts, okay, so we are not really interested in beta 1 hat per se, but we are interested in the y hat. This is the predicted value. We are not interested in what goes into predicting y, but we are predicted value of y. So for instance, when you are looking at stock prices, you want to predict what the prices of a particular stock will be in the future, but you are not really too concerned about what is causing the prices of stocks to go up or down. You are not doing research into the causal effects that are causing the prices to go up or down. You are interested in just predicting, because you want to know whether you want to invest in that stock or not. This is typically the use of, when you use time series data, many times you want to forecast or predict some variable in the future. The third thing that you may want to do is the causal effect. So in this particular case, which is what we will be looking at through this course. So basically we are not interested in y hat, but rather we are interested in beta 1 hat. Okay, so our primary quantity of interest is beta 1 hat. We are not that interested in y hat. So what is this beta 1 hat? That is how much of an effect does one unit change in x1 have on y. So this is the interpretation that we are usually trying to look at. So suppose the school board decided to cut class sizes by 2 students per class. What would be the effect on test scores? So why are we interested in beta 1 hat? Because sometimes, say, cutting class size by 2 students per class means the school would have to hire more teachers, or have more number of classrooms. So that is a expensive policy decision if you are taking the policy decision across all schools to hire more teachers. First of all, you may not be able to hire itself, and secondly, you may want to check out whether there are any other policy decisions that you could take which would also have the same effect or which would increase your test scores. Okay, so you may think of giving the students some classes after school or things like that, giving them access to libraries and books and so on and so forth. So what precisely is a causal effect? So causality is a complex concept, as you may have heard many times, that correlation does not imply causation. Okay, so correlation does not imply causation. So, but we are trying to find the correlation with in its very simple form. The beta 1 is the correlation coefficient between y and x. Okay, so how can we say that it is, how can we look at think of it as a causal relationship? So we introduce the idea of the ideal randomized controlled experiment. Okay, so this is a little involved, and I will go over it slowly. Okay, so we introduce the idea of the ideal randomized controlled experiment. So let us define each of these terms. So the ideal randomized controlled experiments. So ideal means subjects all follow the treatment protocol. There is perfect compliance, no errors in reporting. So you are trying to perform an experiment, and which is, if you remember the experiments in your biology class or in your chemistry class, you will have a control group and you will have a test group, and you will do some treatment on the test group, and you will not do the treatment on the control group, and you will see the effect of whatever, so suppose you are looking at what is the effect of light on the growth of plants. So the test group, all the plants will be put in the light, and in the control group they will be put in the dark, and you will look at the difference in growth between these two plants, and you will do it in a very controlled laboratory kind of situation where nothing else is changed. So everything else will be controlled in a very stringent manner. Okay, also the subjects from the population of interest, the plants that you will choose to put in the dark or the light, are chosen completely randomly, so that you do not choose somehow you do not attribute growth to a particular to light, when in fact the growth should be attributed to better seeds or something. Okay, and having a control group, as we say, so ideal randomized control, you have a control group, and the treatment is assigned as part of the experiments. That is, so the experiment has the idea that the person who is wanting to see or research the difference between two different treatments, or trying to see what effect it has, that person has control over the entire way of how to assign individuals to different groups, what treatments to give. So treatment is assigned as part of the experiment. The subjects have no choice. Okay, so in economics, many times we are hampered by the fact that we cannot actually conduct experiments like this. Our subjects do have a choice, and subjects do not. So what you are thinking, that that X may be affecting Y, but it may actually be that people are choosing to those people who have higher intelligence are choosing to go to. So suppose you have people who are higher intelligence or who are more achievement oriented are choosing to go to schools which have smaller class sizes, because they know that it will affect their enhance their academic performance. So now in this particular case, X is not affecting Y, rather Y is affecting X. So how do you know? It may be that people who would have gotten higher standardized scores are in fact choosing to go to schools with smaller class sizes, and that may often be the case, right? So there may be a reverse causality which is going on over there. So it is important. So if you were able to do the ideal randomized controlled experiment, then in fact you could prove the direction of causality. So imagine an ideal randomized controlled experiment for measuring the effect on test score of reducing STR. In that experiment, students would be randomly assigned to classes which would have different sizes. Because they are randomly assigned, all student characteristics and thus UI would be distributed independently of STR. Okay, so all this, you just choose a certain people randomly, and hence whether they knew English, whether they had English as a second language or whatever it is, it would not matter. They would be randomly chosen, and some people would be put in small class sizes and some people would be put in large class sizes. So thus the error would not be correlated with STR, that is, whatever are the variables that are left over, that would not be correlated with STR. Unlike in the real observational case, what is happening is we are finding that children from immigrant communities are choosing, or they have no choice, or rather they are going to schools because of budgetary constraints or whatever, because of income constraints. They choose to go to schools which actually have larger class sizes. So how does your observational data differ from the ideal? The treatment is not randomly assigned. Students themselves choose to be either in large class sizes or small class sizes. So if you consider percentage English learners in the district, it plausibly satisfies the two criteria for omitted variable bias. It is a determinant of Y, and it is correlated with the regressor X. Thus the control and treatment groups differ in a systematic way. So student-teacher ratio, as we have said before, the correlation between student-teacher ratio and percentage English learners is not 0. So randomization plus control group means that any differences between the treatment and control groups are random. They are not systematically related to the treatment. What is the treatment over here? Basically, whether you are assigned to a small class size, small class, or a large class. Okay, so if it was such that people were randomly assigned to these classes, then there would be you would call it an ideal randomized controlled experiment. But since that is not happening, we also have other variables. So what we do is we just include that variable. We can eliminate the difference in percentage English learners between large control and small treatment groups by examining the effect of class size among districts with the same percentage English learners. If the only systematic difference between large and small class size groups is in percentage English learners, then we are back to the randomized controlled experiment within each percentage English learner group. So basically what we are doing is we are including percentage English learners as another explanatory factor, and when we include that and we look at the contribution of both of these variables, explanatory causal relationship with Y, this way we are controlling for the effect of percentage English learners. So there are three ways to overcome omitted variable bias. One is to run a randomized control experiment in which treatment is randomly assigned. Okay, so so you just take a particular child and randomly assign it to a group, but that is not really possible in real life, where you cannot assign your subjects in the experiment. You cannot assign human subjects to different treatment and control groups. Now you can assign in certain cases individuals that volunteer for a particular clinical trial in, say, testing the effect of a certain group, certain drug on certain diseases. They actually volunteer to be part of a ideal randomized controlled experiment, and in that case they are randomly assigned to the treatment or the control group, and the control group may be given just sugar pills and the treatment group is given the drug, and the person who is taking part in that experiment do not know themselves whether they are in the placebo group or they are in the treatment group. So there they are actually volunteering to be part of the experiment. But in most observational data, that is not true. People do not volunteer to be in the experiment. And another way of overcoming omitted variable bias is by using the cross tabulation approach with finer gradations of STR and percentage English within each group. So this is what we looked at, very small levels of percentage English learners to large levels of percentage English learners. The third one is the one which is most commonly done, in which the omitted variable percentage English learner is no longer omitted. It is included as an additional regressor in a multiple regression. This is done to get rid of omitted variable bias. So in the next lecture we will talk about the population regression model.